La 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 read batch र ask मा पढ्न आँटेको सो each batch मा 5 वटा पेज हुन्छ अनि भित्र मेरो क्वेसन हुन्छ है है as you come to understand various cases that are not always true यहाँसम्म पढिसकेपछि experience system operation will tell you that that is reasonable. If you ask nicely, they might tell you something some frightening stories while nursing their scars of past battles. Working with the distributed system, Working with distributed system is fundamentally different from writing software on a single computer. And the main difference is that there are a lot of new and exciting ways for things to go wrong. In this chapter, we'll get a taste of problems that arise in practice and an understanding of things we can and cannot rely on. In the end of our tasks as engineers, in the end, our task as engineer is to build systems that do their job. That is, meet the guarantees that users are expected, in spite of everything going wrong. In chapter 9, we'll look at some examples of algorithms that can provide such guarantees in a distributed system. But first, in this chapter, we must understand the challenges we are up against. This chapter is thoroughly pessimistic and depressing overview of things that may go wrong in distributed system. We'll look into problems with network, unreliable networks, clocks and timing issue, unreliable clocks, and we'll discuss to what degree they are avoidable. The consequences of this issue are the consequences of all these issues are disorienting. So we'll explore how to think about the state of distributed system and how to reason about things that have happened. फर्स्टमा चाहिँ faults and partial failures. When you are writing a program on a single computer, it normally behaves in a fairly predictable way. Either it works or it doesn't. Buggy software may give the appearance that the computer is sometimes having a bad day, a problem that is often fixed by a reboot, but that is mostly just a consequence of badly written software. Buggy software may give the appearance that the computer is sometimes having a bad day. There is no fundamental reason why software on a single computer should be flaky. When the hardware is working correctly, the same operation always produces the same result, which is deterministic. If there is a hardware problem, that is memory corruption or a loose connector, the consequence is usually total system failure. Example, kernel panic, Windows kernel death, failure to start up. An individual computer with good software is usually either fully functional or entirely broken, but not something in between. This is a deliberate choice in the design of computers. If an internal fault occurs, we prefer a computer to crash complete rather than returning to a wrong result, because wrong results are difficult and confusing to deal with. Thus, computer hides the fuzzy physical reality on which they are implemented and present an idealized system model that operates with mathematical perfection. Thus, computer hides the fuzzy physical reality on which they are implemented and present an ideal system model that operates with mathematical perfection. A CPU instruction always does the exact same thing. If you write some data to memory or disk, the data remains intact and does not get randomly corrupted. This design goal of always correct computation goes all the way back to the very first digital computer. When you are writing software that runs on several computers connected by a network, the situation is fundamentally different. In distributed systems, we are no longer operating an idealized system model. We have no choice but to confront the messy reality of physical world. And in this physical world, a remarkably remarkably wide range of things can go wrong, is illustrated by this anecdote. Anecdote भनेको चाहिँ के हो हेर्नु पर्यो है. In my limited experience, I've dealt with long-lived network partitions in a single data center. In my limited experience, I've dealt with long-lived network partitions in a single data center. PDU, power distribution failures, switch failures, accidental power cycle of router acts, full DC backbone failures, then a hyperglycemic driver smashing info. In my limited experience, I've dealt with long-lived network partitions in a single data center. In my limited experience, I've dealt with long-lived network partitions in a single data center. Power distribution unit failures, switch failures, extended power cycle of overlaps, industry power failure, and hyperglycemic driver smashing is for pivot of DCs as vac, heating, ventilation, and air conditioning system. And I'm not even off scale. In a distributed systems, there may be some part of a key के wrong हुन सक्छ भन्ने मात्रै हो त्यो. In a distributed system, there may well be some parts of the system that are broken. In a distributed system, there will be some parts of system that are broken in some unpredictable way. Even though other parts of system will be, there may well be some parts of system that are broken in some unpredictable way, even though other parts of system will be broken. This is known as partial failure. The difficulty is that partial failures are non-deterministic. If you try to do something in multiple nodes and the network, it may sometimes work and sometimes unpredictably fail. As we shall see, you may not even know whether something succeeded or not, as the time it takes for a message to travel across the is also non-deterministic. This non-determinism and possibility of partial failure is what makes distribution hard to work with. Okay. Main problem of there is a spectrum problem in supercomputing. There is a spectrum philosophies on how large scale computing systems, how to build large scale computing systems. At one end of scale, at the one end of the scale is the field of high performance computing, HPC. Supercomputers with thousands of CPUs are typically used for computing intensive scientific computing tasks such as weather forecasting or molecular dynamics, simulating the movement of atoms and molecules. Okay. At the other extreme end, at the other extreme is cloud computing, which is not very well defined but is often associated with multi-tenant data centers, community computers connected over an IP network, often Ethernet, elastic, on-demand resource allocation, and metered billing. Traditional enterprise data center lies somewhere in those extreme. And supercomputer भनेको monolithic हुन्छ लास्टै ठुलो धेरै ठुलो सिपियुहरू के अरे एकै ठाउँमा मर्ज गरेको होइन अनि क्लाउड कम्प्युटिङ भनेको चाहिँ सबै स्क्याटर्ड अनि अब इन्टरप्राइज डेटा सेन्टर्सहरू भनेको चाहिँ बिचतिर पर्छ अरे दिस फिलोसफिज come very different approaches to handling faults. In a supercomputer, a job typically checkpoints the state of computation to durable storage from time to time. The job typically checkpoints the state of its computation to durable storage from time to time. If one node fails, a common solution is to simply stop the entire cluster workload. After a faulty node is repaired, the computation is restarted from the last checkpoint. If one node fails, a common solution is to simply stop the entire cluster workload. After faulty node is repaired, the computation is restarted from last checkpoint. Thus, a supercomputer is more like a single node computer than a distributed system. It deals with partial failure by letting it escalate into total failure. If any part of the system fails, it just lets everything crash like a kernel panic or simulation. सुपरकम्प्युटरहरू चाहिँ अलिक सिङ्गल अभियसली सिङ्गल जसरी काम गर्छन् या एउटा सुपर बनाएर होइन त दिस वर्क्स would focus on systems for implementing internet service which usually look very different from supercomputers. Many internet related applications are online in the sense that they need to be able to serve users with low latency at any time, making the service unavailable. For example, stopping the cluster for repair is not acceptable. In contrast, offline batch jobs like weather simulation can be stopped and restarted with fairly low impact. Supercomputers are typically built from specialized hardware where each node is quite reliable and nodes communicate through shared memory and remote direct memory access. KRA. Supercomputers are typically built from specialized hardware where each node is quite reliable and nodes communicate through shared memory and remote direct memory access. On the other hand, nodes in cloud services are built from commodity machines which can provide equivalent performance at lower cost due to economy of scale but have higher failure rates. Okay. Large data center networks are often based on IP and Ethernet arranged in cluster topologies to provide high bisection bandwidth. Supercomputers often use specialized network topology. Multi-dimensional meshes and traverses which yield better performance for high performance computing workloads with known communication pattern. The bigger a system gets, more likely it is that one of its components is broken. Over time, broken things get fixed and new things break. But in a system with thousands of nodes, it is reasonable to assume that something is always broken. When the error handling strategy consists simply giving up a large system can end up spending a lot of money on rather than being useful. Okay. If a system can tolerate failures and still keep working as a whole, that is very useful feature for operation and maintenance. For example, you can perform a rolling update, restarting one node at a time while the service continues serving users without interruption. In cloud environments, if one virtual machine not performing well, you can just kill it and request a new one, hoping that the new one will be faster. In geographically distributed deployment, keeping data geographically close to your reduce across reduce access latency. Communication most likely goes over the internet, which is slow and unreliable compared to local networks. So we're going to generally assume that all of the nodes are close together. If we want to make distributed systems work, we must accept the possible of partial failure and build fault tolerance mechanism into the software. In other words, we need to build a reliable system from unreliable components. It's described in the recommendation. We need to build reliable system from unreliable components. It's described in reliability in page 6. There's no such thing as perfectly reliable, so we need to understand the limits what we can realistically promise. Even in smaller systems consisting of only a few nodes, it is important to think about partial failure. Even in smaller systems of only a few nodes, it is important to think about partial failure. In a system, it's quite likely small system it is quite likely that most of the components are working correctly most of the time. However, sooner or later some part of the system will become faulty and software will have to somehow handle it. The fault handling must be a part of software design and you as operator of the software need to know what we would expect from the software in case of fault. It would be unwise to assume that the faults are rare and simply hope for the best. It is important to consider a wide range of possible faults, even fairly unlikely ones, and to artificially create such a situation in your testing environment to see what happens in distributed systems. Suspicions, pessimism, and paranoia pay off. Really realized components. You may wonder whether this makes any sense. Intuitively, it may seem like a system can only be reliable as its least reliable component. Eh, but this is not the case. In fact, it's an old idea in computing to construct a more reliable system from a less reliable underlying base. For example, oh, you're funny, eh? It is an old idea in computing to construct a more reliable system from a less reliable underlying base. For example, error correcting codes allow digital data to be transmitted accurately across communication channels that occasionally get some bits wrong, for example, due to radio interference on a wireless network. Error correcting codes allow digital data to be transmitted accurately across communication channel that occasionally gets some bits wrong. For example, due to radio influence or wireless network. IP, the Internet Protocol, is unreliable to drop, delay, duplicate, or reorder packets. TCP, Transmitter Control Protocol, was a more reliable transport layer on top of IP. It ensures that missing packets are retransmitted, duplicates are eliminated, and packets are reassembled in the order in which they are sent. Although the system can be more reliable than its underlying parts, there is always a limit to how much more reliable it can be. For example, error correction codes can deal with small number of single bit errors, but if your signal is swamped by interference, there is a fundamental limit to how much data can get through your communication channel. TCP can hide packet loss, duplication, and reordering from you, but cannot magically remove delays in the network. Although the more reliable higher level systems is not perfect, it is still useful because it takes care of some of the tricky low level faults, and so the remaining faults are usually easier to reason about and deal with. We'll explore this matter further in the intent argument. चार पेज त भएछ 5 पेज दुई तिन चार पाँच अहिलेसम्म केही क्वेसन नै छैन unreliable networks. As discussed in introduction part 2, the distributed system we focus in this book are shared nothing systems. That is a bunch of machines connected by a network. The network is the only way those machines can communicate. We assume that each machine has its own memory and disk, and one machine cannot access another memory or disk except by making requests to a service over the network. Share nothing is not the only way of building system, but it has become the dominant approach for building internet services for several reasons. It is comparatively cheap because it requires no special hardware. It can make use of commoditized cloud computing services. It can achieve high reliability through redundancy across multiple geographical data centers. It can make use of commoditized cloud computing services. It can achieve high reliability through redundancy across multiple geographical data centers. The internet and most internal network in data centers, often internet, are asynchronous packet network. In this kind of network, one node can send a message, a packet, to another node. Okay. The internet and most internal networks in data center are asynchronous packet networks. In this network, one node can send a message to another node, but the network gives no guarantee when it will arrive or whether it will arrive at all. If you send a request and expect a response, many things could go wrong, some of which are listed in figure 8.1. What is in figure 8.1? Your request may have been lost, perhaps someone unplugged a network cable. Your request may have been waiting in a queue and will be delivered. Perhaps the network recipient is overloaded. The remote node may have failed, perhaps it crashed or it was powered down. The remote node may have been temporarily stopped, perhaps perhaps it is experiencing a long garbage collection pause. See process pause and but it will start responding later. The remote node may have processed a request, but the response has been lost in the network or the network switch has been misconfigured. The remote node may have processed a request, but the response has been delayed or will be delivered later. If you send a request and don't get a response, it is not possible to discern whether A, the request was lost, B, the remote node began, or C, the response was lost. Or it could be coming, or it could be going, The The sender can't even tell whether the packet was delivered. The only option is for the recipient to send a response message, which may in turn be lost or delayed. Their issues are indistinguishable. Indistinguishable. Hazır. Kim var? 14 minutes of kısmına ben dedim mi? Evet. The sender can't even tell whether the packet was delivered. The only option is for the recipient to send a response message, which may in turn be lost or delayed. These issues are indistinguishable in an asynchronous network. The only information you have is that you haven't received a response yet. If you send a request to another node and you don't receive a response, it is impossible to tell why. The usual way of handling this is a timeout. After some time, you give up waiting and assume that the response is not going to arrive. However, when a timeout occurs, you still don't know whether the remote node got the request or not. And if the request is still queued somewhere, it may still be delivered to the recipient even if the sender has given up on it. Network faults in practice today. We have been building computer networks for decades. We have been building computer network for decades. One might hope that by now we would have figured out how to make them reliable. However, it seems that we have not yet succeeded. There are some systematic studies and plenty of anecdotal evidence showing that network problems can be surprisingly common. There are some systematic studies and plenty of evidence showing that network problems can be surprisingly common even in controlled environments like a data center operated by one company. One study in medium-sized data center found about 12 network faults per month, of which half disconnected a single machine and half disconnected an entire rack. Another study measured the failure rates of components like top of rack switches. Another study measured the failure rate of components like top of rack switches, aggregation switches, and load balancers. It found that adding redundant networking gear doesn't reduce faults as much as you might hope, since it does not guard against human error. That is misconfigured switches, which is a major cause of outages. Public cloud services such as EC2 are notoriously for public cloud services such as EC2 are notorious for having frequent transient network glitches. Frequent transient network glitches. And well-managed private data center networks can be stable environments. Public cloud services such as EC2 are notorious for having frequent transient network glitches, and well-managed private data center networks can be stable environments. Nevertheless, nobody is immune from network problems. For example, a problem during a software update for a switch could trigger a network topology reconfiguration. For example, a problem during a software update for a switch could trigger a network topology reconfiguration, during which network packets could be delayed for more than a minute. Sharks might bite undersea cables, and damage them. Other surprising faults include network interface that sometimes drop all inbound packets but sends outbound packets successfully. Drops all inbound packets but sends outbound packets successfully. Just because network links work in one direction doesn't guarantee it's also working in opposite direction. When one part of the network is cut off, when one part of the network is cut off from the rest due to a network fault, that is sometimes called a network partition or net split. In the book, we'll generally stick with more general short-term network fault to avoid confusing with partition size of storage systems. Even if network even if network faults are rare in an environment, The fact that faults can occur means that your software needs to be able to handle them. Whenever any communication happens over a network, it may fail. There's no way around it. If the error handling of network fault is not defined and tested arbitrarily, bad things could happen. For example, the cluster could become deadlocked and permanently unable to serve requests even when the network recovers, or it could even delete all of your data. If software puts in an unanticipated situation, it may do arbitrary, unexpected things. Handling network faults does not necessarily mean tolerating them. If a network is normally fairly reliable, a valid approach may be simple to show an error message to users while a network is experiencing problems. However, you do need to know how your software reacts to some network problems. However, you do need to know how your software reacts to network problems and ensure that the system can recover from them. It makes sense to deliberately trigger network problems and test the system's response. This is the idea behind Chaos Monkey. यो त थाहा छ मलाई. Many system needs to automatically detect faulty nodes. Many system needs to automatically detect faulty nodes. For example, a load balancer needs to stop sending requests to a node that is dead, take it out of rotation. In a distributed database with a single leader replication, if the leader fails, one of the followers need to be promoted to be a new leader. Yes. Unfortunately, the uncertainty about the network makes it difficult to tell whether a node is working or not. In some specific circumstances, you might get some feedback to explicitly tell you that something is not working. If you can reach the machine on which the node should be running, if you can reach the machine on which the node should be running. Unfortunately, if you can reach the machine on which the node should be running, but no process is listening on the destination port because the process crashed, the operating system help will helpfully close or refuse TCP connection by sending RST or FN packet in reply. However, if the node crashed while it was handling your request, you have no way of knowing how much data was actually processed by the remote node. Care. Unfortunately, the system about network makes it difficult to tell whether a node is working or not. In some circumstances, you might get some feedback to explicitly tell you something that is not working. If you can reach the mission on which node should be running, but no process is on the destination port because the process crashed, the operating system will helpfully close or refuse TCP connection by sending a RST or FN packet in reply. However, if the node crashed while it was handling your request, you have no way of knowing how much data was actually processed by the remote node. If a node process crashed or was killed by an administrator, but the node's operating system is still running, a script can notify other nodes about the crash so that another node can take over quickly without having to wait for a timeout. For example, as we especially. If a node process crashed or was killed by the node's operating system, it can nodes are still running. But if the node process crashed or was killed by an administrator, but the node's operating system is still running, a script can notify other nodes about the crash so that another node can take over quickly without having to wait for timeout to expire. For example, if you have access to management interface of network switches, if you have access to management interface of the network switches in your data center, you can query them to detect link failure. If you have access to the management interface of the network switches in your data center, you can query them to detect link failures at a hardware level. Example, the remote machine is powered down. This option is ruled out if you are connecting via the internet if you are in a shared data center with no access to the switches themselves, or you can reach the management interface due to a network problem. If a router is sure that the IP address you're trying to connect is unreachable, it may reply you with an ICMP destination unreachable packet. However, the router does not have a magic failure detection capability either. It is subject to similar the particular its other participants of the network. Rapid feedback and about a remote node. Rapid feedback about a remote node being down is useful. Rapid feedback, carry. Rapid feedback about a remote node being down is useful, but you can't count on it. Even if TCP acknowledges it that package was delivered, the application may have crashed before handling it. If you want to be sure that request was successful, you need a positive response from the application itself. Conversely, if something has gone wrong, you may get an error response at some level of stack. Conversely, if something has gone wrong, you may get an error response at some level of the stack. But in general, you have to assume that you will get no response at all. You can retry a few times, TCP retries transparently, but you may also retry at the application level, wait for timeout to elapse, and eventually declare that node dead if you don't hear it back within a timeout. If a timeout is only sure way of detecting a fault, then how long should the timeout be? There's unfortunately no simple answer. A long timeout means a long wait until a node declared is declared dead, and during this time, users may have to wait or see error messages. A short timeout detects faults faster, but carries a higher risk of incorrectly detecting a node dead when in fact it has only suffered a temporary slowdown due to a load spike in the network. Prematurely declaring a node that is problematic if the node is actually alive in the middle of performing some action, for example, sending an email, and another node takes over the action, it may end up being performed twice. We'll discuss in a chapter. When a node is declared dead, its responsibility needs to be transferred to other nodes, which place additional load on other nodes and the network. If the system is already struggling with high load, declaring nodes permanent dead prematurely can make the problem worse. In particular, it could happen that the node actually wasn't dead but only slow to respond due to overload. Transferring its load to other nodes can cause a cascading failure. Next in place, all nodes declare each other dead and everything stops working. Imagine a fictitious system with a network that guaranteed a maximum delay. Imagine a fictitious system with a network. Imagine a fictitious system with a network that guaranteed a maximum delay for packets. Every packet is either delivered within some time t or it's lost, but delivery never takes longer than d. Every packet is either delivered within some time t or it's lost, but delivery never takes longer than d. Furthermore, assume that you can guarantee that non-filled node always handle request with some time r. Furthermore, assume that you can guarantee that a non-failed node always handles a request within some time r. This case makes your guarantee that every successful request receives a response within time 2d plus r. बुझेँ मैले के भने जानलाई पुग्नलाई डेलिभरीको लागि डी टाइम लिन्छ अरे अनि त्यसपछि रिक्वेस्ट पठाउनको लागि आर टाइम भनेपछि जानलाई डी टाइम अनि उता रेस्पोन्स पठाउनलाई रेस्पोन्स बनाउनलाई आर टाइम अनि त्यसपछि फेरि त्यो आइपुग्नलाई डी टाइम. And if you don't receive a response within that time, you know that either the network or the remote node is not working. If this was to 2d plus r would be a reasonable timeout to use. म काम गर्नु जान्छु केटी हो काम गर्न 5 मिनट जति पर्खदिनु भने हराएको ग्रह मेरो सूर्य अँध्यारो छ म पापी मनको मेरो ईश्वर अधुरो छ Choo choo, choo choo. Kuwaka Buddha, Tili Poriho, Sorigaira, Ratana Naga, Yahai Sachaina, Oh no, not so happy, Antari, was it all? Juno Tara Sejauh Timi Afni Rangaru Ratero Prithivinai Eutanaya Timi Pariho Yasargaina Pratana Garo Yeah, Ishwar China Una NKK. is the only sure way of detecting a fault, then how long should the timeout be? There is unfortunately no simple answer. Timeout, long timeout means a pod echo. When a node is declared dead, the responsibility needs to be transferred to other nodes. Even a pod echo. Imagine a fixed system where a even a pod echo. Unfortunately, must move on. Neither of these guarantees a synchronous network or combined DDIs. That is, if they try to deliver packets as quickly as possible, but there is no upper limit on the time it may take for a packet to arrive. And most server implementation cannot guarantee that they can handle request within some maximum time. For failure detection, it's not sufficient for a system to be fast most of the time. If your timeout is low, it only makes transient spike in round trip times to throw system of balance. It only takes a transient spike in round trip times. If your timeout is low, it only turns on a spike in track and round trip times to throw the system of balance. Transient, let's see. Sorry, not looking. Just when driving on network congestion and queuing. When driving a car, travel times on road networks often vary most due to traffic congestion. Similarly, the variability of packet delays on computer network is often due to queuing. If several different nodes simultaneously try to send packets to the same destination, the network switch must queue them up and feed them into destination network link one by one as external variable. On a busy network, If server not simultaneously try to send packets to the same destination, and output must queue them and feed them into destination network link on the network. On a busy network link, a packet may have to wait a while until it can get a shot. This is called data congestion. If there is so much incoming data that switch queue fills up, the packet is dropped, so it needs to be reset even though is functioning fine. When packet reaches the destination machine, if all CPU cores are currently busy, the incoming request from the network is queued by the operating system carrier. When a packet reaches the destination machine, if all CPU cores are currently busy, the incoming request from the network is queued by operating system until the application is ready to handle it. Depending on the load depending on the load on the machine, this may take an average of the time. In visualized environments, running operating system is often in visualized environments. Virtualized, sorry, give a visualized environment. A running operating system is often paused for tens of milliseconds, while another virtual machine use a similar code. During this time, the VM cannot consume any data from the network, so incoming data is queued back to the virtual machine monitor, further increasing the variability of network delays. TCP performance flow control, also known as congestion avoidance or backpressure, in which a node limits its own rate of sending order to avoid overloading a network or the receiving node. This means that additional queuing in the center, additional queuing at the center before the data even enters the network. Moreover, TCP considers a packet to be lost if it's not acknowledged within some timeout, which is calculated from the observed round trip times. In the lost packets are automatically retransmitted. Although the application does not see the packet loss in retransmission, it does the resulting delay, waiting for the timeout to expire and then waiting for the retransmitted packet to be acknowledged. TCP versus UDP. Some latency sensitive applications such as video conferencing or voice over protocol IP. Some latency sensitive applications such as video conferencing and VoIP uses UDP rather than TCP. It's a trade-off between reliability and variability of delays. As UDP does not perform flow control and does not retransmit lost packets. It avoids some of the reason for variable interrupt delays, although it is still susceptible to switch queues and scheduling delays. UDP is a good choice in situations where delayed data is worthless. For example, in a VoIP phone call, there probably isn't enough time to retransmit a lost packet before its data is due to be played with the care. For example, in a voice over IP phone call, there's there probably isn't enough time to retransmit a lost packet before its data is due to be played over the loudspeakers. In this case, there's no point in retransmitting the packet. The application must instead fill the missing packet's time slot with silence, causing a brief interruption in the sound. Could you move in the stream? The retry happens at the human layer instead. Could you repeat that, please? The sound just cut off for a moment. Hazır. Uh, 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 uh. हेलो। हजुर। म अहिले त पढ्दैछु। भएको छैन, म आफै म्यासेज गर्छु भन्नुहुन्थ्यो, गर्नु भएको छैन, मैले पनि कुरा निकालेँ। दाइले आफै म्यासेज गर्छु भन्नुहुन्थ्यो, अनि मैले अब त्यसपछि मैले कुरा गरेको छैन भनेको। अँ, अब होस्। हजुर। कस्तो किन होस् अनि, अब होस् न अनि। उम्, सन्चै छ। तपाईँको मोबाइल त स्विच अफ भएको भए थियो अरे त, के भएर? कता, कहाँ जानुभएको थियो तपाईँ? ए। उम्, ए, ठिक छ। केही छैन। ए, मेरो साँच्ची ऊ रिजल्ट आएछ, अनि अब पैसातिर निकाल्नु पर्ने मम्मीले भन्नुभएको भन्नुभएन? त्यही बाँकी रहेको, अब स्कुललाई बाँकी रहेको पैसा अरे, अनि त्यसपछि खोइ फर्महरूको पैसा लाग्छ अरे, फर्मको हो कि के सर्टिफिकेटको अलिअलि पैसा लाग्छ होला, 10-15 हजार कति लाग्छ, 5-10 हजार। अब यति पढ्ने हो भने चाहिँ अब निकाल्नु पर्यो कतै, निकालेर कता कता के गर्नु मिल्छ बुझ्नु पर्यो। उम्, तर निकाल्नु भन्दा पनि केही न केही चाहिँ गर्नुपर्छ, किनकि ऊ के भन्छ, इक्विभ्यालेन्स को लागि चाहिँ पठाउनु पर्ने अरे हो, त्यसको लागि चाहिँ अलिकति पैसा चाहिन सक्छ इक्विभ्यालेन्स बनाउनुलाई। खै के फर्म भर्नुपर्छ, के भन्दैछ साथीहरू। भइसकेको अरे। अँ, हो त्यही हो, त्यो गर्नलाई चाहिँ अब सर्टिफिकेट निकाल्नै पर्छ भन्ने छैन, इक्विभ्यालेन्स पनि बनाएर चाहिँ राखिराखो भनेर तिनीहरूलाई पैसा दिएर बनाइदिइराख भनेर भन्ने, अनि त्यसपछि सबै एकैचोटि निकाल्ने, त्यतिर पछि पैसा तिरेर। पर्दैन होला। हुन्छ, अब कुन दिन हुन्छ गएर। कस्तो रहेछ त त्यसलाई, आफ्नै त्यही झन् नेट हाल्दिन पनि नमान्ने। कस्तो रहेछ त नेट हाल्दिन पनि नमान्ने मान्छे भन्दाखेरि। अँ, अँ, हुन्छ। अनि ए साँच्ची सुन्नु न, भाइको ब्याङ्क एकाउन्ट पनि बनाउन गएको मिलेन, म ऊ के अरे गार्जियन बनाउन निकाल्न मिल्दैन अरे, बनाउन मिल्दैन अरे, अनि भाइलाई त अब यता ल्याउने होइन, बरु गाइड बोलाएर तपाईँ अथवा मम्मी झरेर अनि उतै पो बनाइदिने होला त त्यसको ब्याङ्क एकाउन्ट। अह, मैले त्यहाँ ब्रान्च म्यानेजरसँग कुरा गरेको मिल्दैन भनेर भन्नुभयो। त्यही त, अनि यता बोलाउनुको साटो गाइड बोलाउनु, अनि त्यसपछि त्यहीँनेरि आउनु, तपाईँ हुन्छ कि मम्मी को हुन्छ आउनु, अनि त्यसपछि बनाइदिनु। ठिकै छ। छैन गाह्रो अप्ठ्यारो केही पनि, कहीँ पनि जानु परेको छैन। हामीले पैसा हालिसक्यौँ, यहाँ घर चलाउने पैसा सबैजनाले एक एक हजार। अब यो महिना चलिहाल्छ। अनि खानालाई रोजिनाहरूले पकाइहाल्छन्। खाजा पनि बनाउँछन् दिउँसो। त्यो आटाको के अरे एक ऊ ल्याएको थियो पोका प्लास्टिक टन्नै चल्यो। हुन्छ। हस्। 6 मिनट। 6 मिनट। अब यहाँ मेरो काम पर्यो केटा हो, एकछिन पर्दिन है त। हेलो। ठ्याक्क अहिले भर्खर मेसेज गर्नुभयो दाइले, त्यो दाइले। खै हेलो भाइ भन्दै मेसेज गर्नुभएको छ, मैले हजुर भनेर भनेको छु। अब कल चाहिँ गर्दिनँ, त्यही टेक्स्टमा भन्नुहुन्छ होला कल के गर्नु बेलुकातिर। भन्नुहुन्छ होला नि के छ कुराहरू। हस्। हस् हस्। एकछिन नर्मल मात्रै एक्टिभ मेसेज आउन सक्छ। यता होस्। त्यो एउटा queuing delays have especially a wide range of systems limited to maximum capacity. The system with plenty of spare capacity can easily run queues. A system with plenty of spare capacity can easily run queues, whereas a highly Like system monkeys can build it very quickly. In public clouds, multi-tenant data centers, resources are shared with many customers. The network links and switches are even machines network interface and CPUs. When running in a virtual machine are shared, batch workloads such as MapReduce can easily saturate network links. As you have no control over or insight into as you have no control over or insight into other customers' usage of shared resources, network delays can be highly variable. If someone near you, a noisy neighbor is using a lot of resources in such environments, you can only choose timeout experimentally, measure the distribution of network run times over an extended period and over many machines so to determine the expected variability of delays. Then taking into account your application's characteristic can determine an appropriate trade between failure detection, delay, and risk of premature timeouts. Even better, rather than using configured constant timeouts, even better, rather than using configured constant timeouts, rather than using configured constant timeouts, system can continuously measure response time in their variability, jitter, and automatically adjust timeouts according to observed response time distribution. This can be done with a fire a coral failover detector, which is used, for example, in Akka and Cassandra. TCP transmission timeout also work similarly. Because here no shortcuts how to get rid of hiccups. हजुर हजुर खाना खाने टाइम भएको ल Bye bye, Beth.